So it's about that time. So I'm going to go ahead and get started. My name is Sean, and I'm the dynamics tutor for SARC, and I'm going to be going over the review today. I was told by the professor that the exam is mainly going to cover 15, 16, and 17, with I think there's like a few, like 2 and 15 and 1 and 17 that's not included. So I focused mainly on those. It says 1621 here, for example, but it's actually your chapter 15. So I'm going to start out with this problem. Mainly going to be working problems throughout just because I figured that's the easiest way to do it since there's so much material. So this is just a angular acceleration problem. And so I'm just going to start out by writing the relation. We're going to integrate. Plus 0.75 dt. You end up with you get an angular acceleration of 9.10 radian per second after your integration. And as for the velocity and acceleration of the block when t is equal to 2 seconds. So we have velocity is equal to the angular acceleration times the radius, or the distance. It's going to be 9.1 times 0.15 meters, which gives you 1.37 meters per second. And it's just another formula. It's going to be the tangential acceleration only, right here, which is going to be equal to the angular acceleration times r, which is equal to 0.6 t squared plus 0.75 times 0.15, or r. And it should give you an answer of 0.472 meters per second squared. So to start off with an easy one, just basically plug and chug. If you know your formulas, it's pretty simple. This problem's a little bit more tricky. It's going to be a crankshaft AB is rotating at a constant angular velocity of 150 radians per second. Determine the velocity of the piston P when the angle theta is equal to 30 degrees. So this is the angle theta. So that's 30 degrees. And so you want to start out here is you want to write your position function of x, or which is going to be your p. So you're going to start out by breaking it up and doing this part, and then adding it to that part. So for the first part, you're going to get 0.2 times cosine of theta plus, and that's going to be you have the hypotenuse, which is 0.75. So you're looking for this value. So you're going to take the square root of 0.75 squared minus 0.2 sine theta squared. Now when you take the derivative of that, which would be your velocity, you get negative 0.2 sine of theta plus 1/2 0.75 squared minus 0.2 sine theta squared, so the negative 1/2 times negative 2 0.2 sine theta and 0.2 cosine theta which ends up being equal to negative 0.2 angular acceleration times sine of theta subtracted by 1/2 0.2 squared angular acceleration sine of 2 theta over the square root of 0.75 squared minus 0.2 sine of theta. So now you have your velocity function. You're going to plug in the values you were given. So theta equals 30 degrees. Angular acceleration is 150 radians per second. You get velocity of p is equal to negative 0.2 times 150 multiplied by the sine of 30 degrees subtracted by 1/2 0.2 squared times 150 times the sine of 60 degrees all over 0.75 squared minus 0.2 sine of 30 degrees squared, which gives you a value of negative 18.5 feet per second, or 18.5 feet per second to the left. Again, something pretty simple, just using the formulas for the angular acceleration, and this is going to be significantly more difficult than that one. So 16.5.1, the bar is confined to move along the vertical and inclined planes. If the velocity of the roller at A is 6 feet per second when theta is equal to 45 degrees, determine the bar's angular velocity and the velocity of roller B at this instant. So, first thing, I'm going to just draw a little diagram. Five feet up here. All right. So just going to try to do some relations just to start with. So the first relation off the geometry we can do is that SB cosine of 30, which is going to be that, is equal to 5 times sine of theta. You have simplified S of B is equal to 5.774 sine of theta. If you take the derivative of that, you get 5.774 cosine theta, theta dot. You also have 5 cosine of theta is equal to SA plus SB sine of 30 degrees. Take the derivative of that, you get negative 5 sine of theta, theta dot is equal to SA dot plus SB dot sine of 30. This is going to be 1 and 2. So from there, I'm going to combine 1 and 2 to give you negative 5 sine of theta, theta dot is equal to negative 6 plus 5.774 cosine of theta, theta dot sine of 30 degrees. Simplifies to negative 3.536 theta dot equal to negative 6 plus 2.041 theta dot. And remember that theta dot is equal to alpha. So we have angular acceleration is equal to 1.08 radians per second. Then from there, you can plug that in to our equation 1 to get SB, which is the velocity of B. And that's going to be 5.774 cosine of 45 degrees multiplied by 1.076, which is equal to 4.39 feet per second. All right. Honestly, I'm not sure if you guys have covered this. Have you guys covered rotating about a point at a certain instant in time?
Yeah.
Okay. Perfect. What 1684 is mainly focusing on. All right. So you have the portion of this little thing is equal to, or is rotating at 6 radians per second. It's asking for the velocity of point B and the angular velocity of AB at the instant shown. All right. Start with rotation about a fixed axis. I'm going to draw (6 radians per second). We have other thing we're looking for. And this distance is going to be equal to 0.6 divided by sine of 30. It's going to be equal to 1.2 meters. So from there, you can get some relations going. So you can put the velocity of c, this is from that equation. This is going to be equal to angular velocity of CD multiplied by RC. That's going to give us 6 times 0.6, which is equal to 3.60 meters per second to the left. And then we can get VB from that, which is going to be, or we can put a relation for a velocity of B. To RB is equal to WAB times 1.2 All right, so that's what we're going to solve for at the end. And going back to general plane motion. Going to draw another figure over here on the side. All right, so there's our free body diagram, and from there we have that RC, IC equal to 0.6 times the tangent of 30 degrees, which is equal to 0.3464 meters. And similarly, RBIC is equal to 0.6 over cosine of 30, which comes out to 0.6928 meters. And from there, we can find the angular velocity of BC. It's going to be equal to VC over RC IC, which is 3.60 over 0.3464, which gives you 10.39 radians per second. And from there, you can get the velocity at B is equal to angular acceleration of BC times the distance of B relative to the fixed axis of rotation. It's going to be 10.39 times 0.6928. And you get that VB is equal to 7.20 meters per second, 60 degrees from the horizontal. And you take this, and you can plug it back into this equation up here. You're going to get 7.20 is equal to angular velocity of AB times 1.2. Get the angular acceleration at AB is equal to 6 radians per second. It's going counterclockwise. All right. So that does it for that chapter. Mainly focusing on the others because I believe you guys had an exam already on a good part of chapter 15, right?
I think so.
Yeah, okay. So this is going to be chapter 16 stuff. So it's going to focus on equations of motion and moment of inertia and all that good stuff. So this problem is by far the most difficult we've done so far, and lengthy. All right. The uniform slender rod has a mass m. If it is released from rest when theta is equal to 0 degrees, determine the magnitude of the reactive force exerted on it by pin B when theta is equal to 90 degrees. So first we'll do a free body diagram. The weight. L over 3. All right. So this is, the weight is coming from the center of gravity, which is not at the pin. It's going to be off by 1/6 of the length of the bar. And we also have B. All right. I have our free body diagrams. So I'm going to start out by putting that rotates about B. Therefore, angular acceleration times the distance from the center of gravity is equal to angular acceleration times L over 6. Equal to alpha squared times L over 6. I have mass moment of inertia. It's 1/12 ml squared. So all of that combined, you want to put your moment equation here. It's just going to be equal to the sum of the moment which is negative mg cosine of theta all over 6 is equal to negative m times the angular acceleration times L over 6 times L over 6 minus 1/12 ml squared times the angular acceleration. Simplifying gives you 3g over 2l times the cosine of theta. It's equal to the angular acceleration. This equation can also be obtained by applying sum of the moments around B is equal to the moment of inertia at B times angular acceleration. And the moment of inertia there is going to be 1/12 ml squared plus m L over 6 squared, which simplifies to 1/9 ml squared. Put that in, you end up getting MB equals negative mg cosine of theta all over 6 is equal to negative 1/9 ml squared you get the same thing. which is useful for other problems where you might not be able to find one or the other. So we're going to plug this into our force equation. It's going to give you mg cosine of theta minus b of t, reaction force, is equal to mass times that equation we got, 3g over 2L cosine of theta times L over 6. And that's going to simplify to giving you BT is equal to 3/4 mg cosine of theta. And in the normal direction, do the same thing. It's going to give you Bn minus mg sine of theta is equal to the mass times alpha squared L over 6, which is equal to, or Bn is equal to 1/6 mass times alpha squared times L plus mg sine of theta. Pull out a second piece of paper. So here, we can find the angular velocity by integrating. You can take alpha d alpha is equal to integral of and after integrating and plugging in your two boundaries, you can simplify it to be equal to 3g over L times sine of theta. And that's all going to be under the square root. So, using our initial values we were given, theta is 90 degrees, and we just got that the angular velocity is the square root of 3g over L, and obviously sine of theta goes to 1. You can substitute this into the equations we got earlier. Get BT is equal to 3/4 mg cosine of 90, and that's equal to 0. And you have Bn is equal to 1/6 m 3g over L times L plus mg sine of 90 degrees. And that's going to simplify to 3 over 2 times mg. And you can say the force is at B is equal to bt squared plus bn squared, square root of 0 squared plus 3 over 2 mg squared, and you end up getting 3 over 2 mg. And if you look at it, at a free body diagram, it makes sense that when theta is 90, you're going to end up with this thing is going to be going like that, and the force that's going to be going, bt is going to be going in this direction. Bn is going to be going there. So it makes sense, it kind of checks out logically that your bt is going to be 0 at that point, and your normal is going to be 3/2 of the weight, which is obviously the weight, and then half the weight is due to the rotation being undergone. So that's that problem. And this problem is pretty quick. It's just a simple way to kind of, if they were to give you the radius of gyration, it kind of shows you how easy it ends up being because of it. So sum of the moment is actually equal to the radius of gyration multiplied by the force. And you have sum of the moment is equal to times that. You end up getting 15, which is the force, multiplied by the radius, is equal to 80. Since 80 is pounds, you're trying to get it from lbf to lbm, and then multiplied by 0.4 squared for angular acceleration, and for our length. You get that the angular acceleration is equal to 18.87 radian per second squared. You can solve for that. It's going to be 25 is equal to 5 plus what we just solved for times t, and it's going to simplify to 1.06 seconds. And all right, I'll just go over some stuff before. We're going to take a little break in about 10 minutes or so. Before that, I just have some I don't know, when I took dynamics, I knew that one of the things I had the toughest time with was kind of knowing when to use certain ways of solving a problem compared to other ways that seem to be, you could do either one. But there are a few times when you should use a specific type of way of solving a problem. So for me, the two toughest things to determine was between energy and momentum. So kind of wrote down when to use. So for energy, You want to do it when objects change height. Other objects start moving. And or springs are present. You usually know it's an energy problem when there's angular velocities that are mentioned that are either given or asked for, but there's no angular accelerations mentioned. Usually if you see something like that, you know you're looking for an energy problem. So, and then for momentum, number one thing is collisions. If there's a collision that is undergone at any point in the problem, then you know that there's going to be some energy lost. And if there's energy lost, you can't use the conservation of energy, which means that your energy equations aren't going to work. So for the most part, I think that unless they specifically tell you to work one way or the other, in my opinion, the energy way of doing things is typically a lot easier. But you can't do it if there's a collision, because it's just not going to work. So, yeah, I'll write loss of energy. So those are pretty important to remember. Besides that, here, I'll put some more down. In general, the moment of inertia, you want to use it when something is going to rotate or is rotating. And you want to find a force F, a moment M, or an angular acceleration A. And then another big general just theory topic is remember when you're using energy equations and you're using work, keep in mind that it's the force times the distance. And keep that in mind when you're trying to figure out if something should be positive or negative. It's whatever you set the standard to be at the beginning of the problem with your axis, which direction is positive, because that's going to make a big difference as to whether the work is going to be positive or negative. And besides that, it's also important to remember that the force of friction is always going to be negative. Kinetic energy. All right, so you know that T in general is equal to, most people know the translation. And this is for rotation. And then if it's moving about a fixed point at an instant, you can combine them both. At this velocity of the center of gravity, and it's going to be the moment of inertia at the center of gravity. So that's pretty big. A lot of people forget to add them all together and kind of just choose one or the other. It's definitely a big issue I see. I guess I think it's a pretty good time to take a quick 10-minute break. It's 4:45, so I'm gonna step out for a minute, and we'll start back at 4:56 now. All right, welcome back. Just gonna start. So for the rest of the time I have, I'm gonna focus on chapter 17 stuff. So it's gonna be mainly focusing on plane motion of rigid bodies, energy and momentum analysis. So the main equation you're going to use is T1 plus U from 1 to 2 is equal to T2. Went over the kinetic energy already. All right, I'm just going to dive into these problems now. I have them. All right. Okay. So 1711. At the instant shown, link AB has an angular velocity of 2 radians per second. If each link is considered as a uniform slender bar with a weight of 0.5 pounds per inch, determine the total kinetic energy of the system. So, I'm going to write some equations down. T is equal to 1/2 mv squared plus 1/2 mw squared. I, of course, is 1/12 ml squared. So, I'm going to start with obviously we had the angular acceleration of AB is equal to 2 radians per second. So we can, using this equation, get the angular acceleration of BC is equal to 6/4 equal to 1.5 radians per second. You can get that the velocity of C is equal to 1.5 times 4 times the square root of 2, which is from our so we get velocity of C is equal to 8.4853 inches per second. Now to find the distance from center of, or the rotation to the center of gravity, you have, it's going to be the square root of 2 squared plus 4 squared is gives you 4.472. And draw a free body diagram quick. That's your G right there. So going back, we can see that Vg is equal to the angular velocity times 4.472. It's going to give us 6.7082 inches per second. And then we can get the angular velocity of DC is equal to 8.4853 over 5. So yeah, it's VC over 5, which is equal to 1.697 radians per second. So you have ultimately we're going to have to find the total kinetic energy of the system. So we're going to take it down here. So using our equation, we put up top 1/2 mv squared plus 1/2 moment of inertia times the angular velocity squared for each of the parts of the beam. We're going to have 1/2 times third, 3 times 0.5 over gravity times 3 over 12 squared times 2 squared plus 1/2 4 times 1/2 over 32.2 to get the mass, and it's the velocity. It's the velocity at the center of gravity. This is to get it to feet squared. Plus 1/2 times 112 m times L, 4 over 12 squared times the angular velocity squared plus 1/2 times a third of 5 times 1/2 divided by 32.2. Get the mass. Times 512 squared times the angular acceleration squared. And all of that is going to simplify to 0.0188 feet per pound. Whew. All right. Moving on, got like 3 more problems. All right. 1836. At the instant shown, the 50-pound bar rotates clockwise at 2 radians per second. The spring attached to its end always remains vertical due to the roller guide at C. If the spring has unstretched length of 2 feet and a stiffness K of 6 pounds per feet, determine the angular velocity of the bar at the instant it is rotated 30 degrees clockwise. So, draw a Freebody diagram. It's going to be the datum. It's the spring force. Can have the weight acting in the middle. And then again there. This distance is going to be, if we have a total distance of 6 feet, it's going to be 6 feet times the sine of 30 degrees, which simplifies to 3 feet. And this is going to be half of that. So that distance is 3. It's going to be 3 sine of 30 degrees, which is 1.5 feet. So, I have a Freebody diagram, and have T1 plus V1 is equal to T2 plus V2. That's just our general conservation of energy equation. And for T1, we're going to have 1/2 times, this is going to be the mass, 50 over gravity, times the length squared, times 2 squared, which is you're going to add that to 1/2 6 4 minus 2 squared, which is potential energy due to the spring. And you have, again, it's going to be 1/3 32.2 times 6 squared times angular velocity plus 1/2 is the spring force at position 2. It's going to be going to be 7 minus 2. Squared minus 50 times 1.5. And solving for that, you get 2.30 radians per second. All right. So moving on to this problem, 1852. The two bars are released from rest at the position theta. Determine their angular velocities at the instant that they become horizontal. Neglect the mass of the roller at C. Each bar has a mass m and length L. So, I'm not actually solving for anything, we're just writing relations. You can come in. All right, so Freebody diagram, have weight AY and theta all right. We have potential energy datum at A. So when the links AB and BC are at their initial position, their center of gravity is located at L/2 times sine of theta. Above the datum. Their gravitational potential energy at this position is mg L/2 sine theta. So that's going to be V1 is equal to 2 times mgL/2 times sine theta, which simplifies to mgL sine theta. And at V2, we have that we're looking for the instant that they become horizontal, which means that there's not going to be any distance between the datum and the center of mass in the horizontal direction or in the vertical direction. Therefore, V2 is going to be equal to 0. And then looking at kinetic energy, so we have when links A, B, and BC are in the horizontal position, then VB is equal to the angular velocity times the length, which is it's directed vertically downward since link AB is rotating about fixed point A. All right. Link BC is subjected to general plane motion, and its instantaneous center of zero velocity is located at point C. Thus, the velocity of B is going to be equal to the angular velocity of link BC times the distance from B to the instantaneous center. You can also rearrange that to be the angular velocity of AB times L is equal to angular velocity of BC times L. Because angular velocity of AB and BC are equal. The mass moment of inertia for link AB and BC about point A and C is what we're going to look for next. So AB about A is equal to IBC about C, which is equal to 1/2 ml squared plus ml over 2 squared, which comes out to 1/3 ml squared. Since links AB and CD are at rest initially, then you have that T1 is equal to 0. T2 is going to be given by 1/2 the moment of AB about A times the angular velocity squared of AB plus 1/2 moment of inertia of BC about C times the angular velocity of BC. You can simplify that and get 1/2 times 1/3. Oh, this is going to be equal to 1/2 times 1/3 ml squared times angular velocity squared plus 1/2 times 1/3 ml squared angular velocity squared for AB and BC. So you can simplify all that to be equal to 1/3 ml squared angular velocity squared. And then we have conservation of energy. T1 plus V1 is equal to T2 plus V2. So we just plug in the values we got, or the equations we got. We have 0 plus mgl sine of theta is equal to 1/3 ml squared times the angular velocity squared plus 0. And solving for the angular velocity, which is the same at both, we have square root of 3g over L times the sine of theta. All right. Going on to the next problem, 1862. 50-pound wheel has a radius of gyration about its center of gravity g of 0.7 feet. If it rolls without slipping, determine its angular velocity when it has rotated clockwise 90 degrees from the position shown. The spring AB has a stiffness K equals 1.2 pounds per feet and an unstretched length of 0.5 feet. The wheel is released from rest. So we have K is equal to 1.20 pound per foot, and LO is equal to 0.5 feet. The wheel is released from rest. All right. So we have our conservation of energy equation. And it's released from rest. So we have that T1 is equal to 0. For V1, we know that we have the spring, which is going to be 1/2 times K times L minus L0. So what we need to find is we need to find this distance. This is 3 feet. .5 feet. So we have L is equal to the square root of 3 squared plus 0.5 squared. We just go ahead and put that in. V1 is equal to 1/2 times 1.20 times square root of 3 squared plus 0.5 squared minus 0.5. That's going to be squared. We have T2 is going to be equal to 1/2 ml squared times angular velocity squared plus 1/2 m squared so plugging in our values for that, we have 1/2 50 over 32.2 times the radius of gyration squared times angular velocity squared plus 1/2 50 over 32.2 and our V2 is going to be the spring constant again. And since it's going to be rotating 90 degrees, it's going to be so that, let's see, we get that distance there, it's going to be rotating, so it's going to be the original L we had, which is the square root of 3 squared plus 0.5 squared minus the 0.5 feet, since it's going to be rotating to be okay. So that ends up giving us, for the same thing up here, we have k is 1.20 and square root of 3 squared plus 0.5 squared minus 0.5 minus 0.5 squared is equal to 1/2 1.20 9292 minus 0.5 squared. So we plug that into our equation over here, we end up getting 0 plus 1/2 times 1.20 times the square root of 3 squared plus 0.5 squared minus 0.5, all of which is squared, is equal to 1/2 times 50 over 32.2 times 0.7 squared times angular velocity squared plus 1/2 50 over 32.2 for the mass times w squared plus 1/2 1.20 0.9292 minus 0.5 squared, and that can be simplified to get 1.80 radians per second. All right. Let's see. Looks like that is the last practice problem that I had. Going to just go over some of the important aspects of the chapters, the theory really quickly, and then go over some test taking tips, and then close it out. So put here theory. see what Alright, so the instantaneous center of rotation is going to be the point where the perpendicular distance from the velocity vectors intersect. We have absolute and relative acceleration. You have AB and AA. It's going to be AB relative to A. This is AB relative to A, the normal direction, and AB relative to A in the tangential direction. So, few formulas here get kind of tricky. These are just the vectors plus A, B relative to A. B relative to A. The tangential direction is equal to rotational acceleration crossed with distance of B relative to A. It's equal to that. And in the normal direction, we have angular velocity squared times the distance of B to A is equal to R times angular velocity squared. All right. Chapter 16. I think the important thing about this is just realizing that you have to look for the forces and these acceleration equations that we have that we're usually given to in the angular acceleration or the angular velocity, and we have to equate those for this side. So usually from and this side tends to be given from external forces and weight as well as reaction forces. Then here we have the moment of gravity the sum of the moment around the center of gravity is equal to the rate of angular momentum about the center of gravity. Remember, rotational momentum is equal to distance cross with the velocity times the change of mass. So it's the moment of inertia times the angular velocity. And the rate of that is equal to the moment of inertia times the angular acceleration. Remember that ATs are equal to RA, AN is equal to RW squared, and for rolling motion, we have without sliding R theta rolling, sliding, impending. We have and then obviously rotating and sliding. We use the coefficient of, or the kinetic coefficient of friction times the normal force. Remember to use the normal force and not the weight, especially if it's in an incline. For example, if it's 30 degrees, you have a ball with what mass of, I don't know, just a mass, then your normal force is going to be in that direction. So it's going to be what? Then you'd multiply that by the coefficient of friction, kinetic friction. And then acceleration of mass center. So you need to break it into the tangential and the normal components. Let's see if I have anything else to go over. All right, I think that is going to cover it for the new material. Just going to go over some tips for the exam. So obviously, to start off with, going to be get a good night's sleep and eat really good. Don't be like me. Barely had any sleep recently. And then number 2, I would say definitely work all the different types of problems and be ready for anything, because I believe I saw there was 3 or 4 problems, or maybe it was 4 or 5 problems on the exam. So work wide variety of problems. Because you can't really afford not to have seen a certain type of problem that's coming on the exam. You want to at least have an idea of where to go when you start with it. And you want to know when to use which type of analysis, which I covered earlier. That will save you a lot of time when you're sitting there, keep you from starting to work the entire problem with one method, and then you realize something doesn't make sense or something's off. Number 4, keep up with units. It's probably the number 1 thing that has helped me out in tons of different classes. So anytime I forget a formula or don't know which formula to use, and I look at what I have and what I'm looking for, if I know the units of everything, I can kind of figure out, basically make a formula from what I know if it's not too complicated. So that's pretty important. And in my tutoring sessions, I know that one of the main things a lot of people are having issues with was just knowing how to set up a problem, how to kind of draw the Freebody diagram and get a good mental picture of the problem. And what I've been telling them to do, if they're having trouble with that, is just to work a whole ton of problems, but not really work them, just kind of put the setup down. If you guys have Chegg or the solution manual, or however you can kind of just look at an example of a Freebody diagram, so you don't have to spend all the time working out the entire problem. I think that's really, really worth it, because it's kind of a buzzkill when you don't even set the problem up the right way and you have all this work and your answer's totally off, but you did everything right except one thing in the setup. So put practice setting up problems. So check Freebody diagram, equations, and your strategy. Move on. Number 6, I would say definitely don't try to cram for this exam, because there's way too much material for you to do that effectively. I think that your best bet is to start out with a theory basis, and then directly afterwards apply to problems. And make sure you know why you used that specific method. Number 7, probably my last one, is going to be to take a deep breath and relax. Because at the end of the day, this exam is not going to be the end of the world. And with that, I think I'm going to go ahead and wrap up. And thank you guys for looking at the stream online if you guys are there, and for those of you that came in. And I guess wish you guys luck on the exam. And I'm going to put this QR code up there so you guys can do a quick little survey. For those of you at home and stuff, just go on there and let us know how you guys feel. And with that, thank you guys.